Right, the next talk is towards Copeland optimization in combinatorial problems, and Alexander Schiendorfer will give the talk.
All right, so I'm Alex, and I'm going to talk about Copeland optimization. And this is strictly speaking on the modeling side. So I want to propose a novel kind of objective to go for, which is heavily inspired by social choice theory. So what is a Copeland score in the first place? Let's look at your favorite combinatorial optimization problem that I've put here in a very comical way, so you can think of a scheduling problem of ERP. And the interesting part here is you have different valuations that represent happiness or some kind of utility. So the first agent here expresses their preference in terms of a 0 to 1 satisfaction, so likes the red solution most. The second one expresses their preference in terms of penalties, so likes the violet one most. And the third one uses something even more esoteric, just a set of violated constraints ranging from the empty set being the best. And this is, although this seems a bit abstract, think of people having a desire for expressing their preference in terms of stars, 5-star ratings, the other ones express it in terms of money. And it's not always clear how to convert this. Fortunately, the social choice theory people have a plenitude of methods that work purely ordinally. So what we do here is form ballots that are essentially just weakly ordered lists of the options. This theory really comes from political elections. So we just have a relatively small number of options, whereas here I want to propose to use this for combinatorial problems. So what we recognize here is voter 1 ranks the red one at the top, voter 2, the purple one, etc. So at this stage, everything is just ordered. We don't have any currencies, any units anymore. And then what we can do is form what's called a tournament, a pairwise majority tournament, to be precise. So we list out all the options in this kind of diabolical pentagram here, and we just make duels, pairwise majority duels. So for instance, if we compare the violet one and the blue one, so theta 3 and theta 1, we see that voter 1 and voter 2 rank violet above blue, but voter 3 thinks the opposite way. So in total, violet wins by 2 to 1. And ideally, you'd like to have a candidate that wins all their duels. Such a candidate would be called a Condorcet winner, named after the Marquis de Condorcet. But in reality, that doesn't always exist. So the next best thing we would like to do is look for an option that wins the highest number of duels. And this is the Copeland score, which essentially, and this is quite nice, it works with weakly ordered preferences. So you count the number of options that you strictly win against, plus half time you tie. So we don't have any ties in this little diagram, but that's the way the Copeland method operates. And naturally, being optimizers, we want to get the solution that has the highest Copeland score. And actually, even though it's called the Copeland score, it goes back to the 13th century philosopher Ramon Lull. It's sometimes also called Lull's method. So you might wonder, this is really old related work, but they didn't have optimizers back then. So that's what we want to change. So why Copeland? Why is that the purpose of this talk? First of all, it is Condorcet complete. So if there is a Condorcet winner, it will get picked, which is generally a nice property to have. And it's a natural extension of Condorcet if there is no winner. It can model weak orders and represent and really just deal with orders without any utilities. On the other hand, it loses information about the margin of victories. So it really throws all that away, and Borda would be a possible solution here. But there are plenty of other electoral systems, such as the Schulze method or border and all of those. So in a nutshell, this is what we want to get rid of. As Guido put it nicely, I don't want to model with integers and I don't want to sum them up for objectives either. I also don't want to do things like maximize the highest dissatisfaction. Because I'm looking at situations where I really cannot compare easily the utility of one agent with that of another one. The high-level goal is to just explore novel preference aggregation methods borrowed from social choice. And yeah, that is, so ideally in a modeling language, I can just write down, maximize my Copeland score and run. So in terms of the related work, the combination of CP and voting has received a little attention, mostly by the groups around Francesca Rossi and Kirsten Brent-Venable, that propose to use sequential voting. So you would say for X, what should be the domain value of X, and then given the value of X, what should be the domain, what should be the assignment for variable Y, etc. This has some nice properties in lifting election theoretic results, but it's kind of myopic though. So you can't really backtrack, and once you've picked the wrong person into office, there's no way to change that. You could say this is just a classical multi-objective optimization problem. You minimize the distance to some utopian points, or you sample the Pareto frontier. But this becomes undecisive the larger number of utilities have, because you face kind of this cursive dimensionality situation where if you just have enough voters, any option will become a winner. Rawlsian, proposed by John Hooker and colleagues, has the drawback of utilities having to be commensurable. And we've had a simple proposal on Condorcet voting at CP19, but it's not really clear what the objective should be if there is no Condorcet winner. And this is kind of what we want to patch here. However, so it's a bit of a philosophical question if you think that Condorcet is a valid objective. But if you choose to do so, you still face an exponential number of candidates. So every solution is a candidate. And I'm already looking at the group of Gilles. This is one of the situations where I want a representative sample, and I cannot enumerate all of them. Little spoiler ahead. But also determining the Copeland score is quadratic, and finding the exact Copeland score would really require access to all solutions. So we strive for a population-based local search approach using sampling. So what does it look like? We start with the first couple of solutions, our initial solution pool. We take sample ballots. So we really have our voters just give us the rankings over a subset of all the solutions. We do this tournament across the sample and figure out which one is winning. We then, in order to keep the sample pool relatively small, we delete solutions that perform weakly. So here, this theta 4, the green solution, was dominated by all of the others. So we threw it away. And then we have to explore new solutions. We have to get fresh ones and then keep going with our search, where we can use default search or employ some form of diversity constraints, something we've heard a couple of times today as well. That will update our solution pool and rinse and return, right? The challenges are, and actually that's what I think makes this problem kind of interesting, is so what we see here is a very small scheduling instance, which we could solve completely, so we could enumerate all solutions. And what you see on the x-axis is just the chronological order of the solutions. On the y-axis, you have the normalized Copeland scores. And if I asked you, well, this particular solution 957, how good is that? How good is that solution? it will really depend on whether I'm asking you, once your solution pool consists of these couple solutions that you've explored, or if you were here you think it is really a good one, you estimate that this is probably a Copeland winning solution. It's better than most of the others. And this is even worse if you took one of those solution pools. Here, we were relatively lucky that the default search strategy just happened to produce very good solutions up front. The other part that's interesting is I hope to exploit these kinds of distributions of Copeland scores that we've recovered. Most of the time, they seemed normally distributed. So we have a moving target. In contrast to a normal CP or MIP model, we cannot write down the objective function, and we have just this expression being a function of all the decision variables. Our Copeland score really depends on all the other solutions in our pool, and that pool changes. For an accurate estimation of Copeland, we need a representative sample. We kind of need bad solutions to know that we are good. So if we are in just a pool of only good solutions, we really underestimate the quality of our candidates. Conversely, if we are only working with bad solutions, the one-eyed among the blind is just really looks much better than it is. But of course, at some point, we want to zoom in on the good ones. To help with this, we've used a slight trick in Minizinc. So we've tried to maximize diversity by simply asking for the next solutions to have a high summed absolute distance to the previous solutions, which is kind of generic, but as it turned out, didn't really capture the nature of diversity in terms of the objective values quite enough. But we've gave it a shot nevertheless. So we evaluated those models on a couple of classical combinatorial problems that we adapted to this multi-agent setting. So it was vehicle routing with time windows where we've had preferences for the individual participants. Job scheduling, where some of the agents were job owners and they wanted to maximize their jobs. Project to student assignment, or photo placement, where you'd like to be close to your friends and far away from your enemies. And we dealt with pretty small instances to have oracles that tell us how close are we in terms of the Copeland score. In terms of the metrics, we've used two different ones to assess the quality of our local search. The first one is the Copeland gap. The Copeland gap tells us, well, what's the solution that we've picked using our local search? This is this purple one here. And we compare it to the actual Copeland winner that we know because we've calculated them all. And we compare the actual ground truth Copeland scores. So this really tells us, okay, if the gap is 0, we picked the Copeland winner. If the gap is larger, we picked another solution that is just worse. And the second one, to look for a different quality, is how good was our estimation? How good was our sample? So we take we just consider the sample winner, so not the ground truth winner here, and we compare what we believed its Copeland score was. So we believed its Copeland score was 0.9, but in reality it was 0.6. So we are very confident in picking the wrong solution. That is the two metrics that we were interested in. We ran these experiments on the following problems and instances. And first of all, the one thing we note that diversity maximization didn't have a clear advantage. It was helpful in determining the Copeland winner for vehicle routing. But in general, the gaps and errors were relatively low already with the default search. Sometimes even in photo placement, we really got far off with the diversity maximization. So we have a pretty high gap of the chosen winner, and the error of what we believe it is also pretty high. So this is like Real Madrid just playing a lot of third-tier clubs and believing that this was representative of the Champions League, so to speak. So in conclusion, but still we believe that this is a direction that we can go. In small instances, it seemed okay. We got solutions that were practically interesting. What are the real benefits? So in terms of our modelers, we can tell them, okay, use whatever preference formalism you like. So give stars, thumbs up, 0 to 1. We don't do any crazy business normalizing those values. That's the true advantage. So coming back to the units from yesterday, we can have everyone have their own unit, and we won't have accidental bias by just crunching the numbers. That's the true benefit of this. The drawbacks are the margins are still ignored. Our quality depends heavily on the quality of the sample, but I know maybe some approach that we've heard today, which should be really interesting to try. And the relationship to other multi-objective optimization is just underexplored. We have to do more work here. We want to incorporate better diversity search, perhaps more problem-specific one. So compared to the previous talks, we don't just care about uniform sampling, but we actually care about having the same distribution of objective values in the sample than we would have in the true problem. We would like to use these distributions to devise stopping criteria, and we want to work with other social choice functions, such as order or the Schulze method, or things like that. All right, so thank you.
The clarification. Is the other preferences defined over the scheduling solution?
Yes, exactly. So you can for example, in scheduling we said we list every job, give it a numerical value, and our utility is the sum of all the jobs that were actually planned for us. We allowed cancellations.
Yeah, and that will give you a quality of the solution, like a real value, right?
Yes, but just for one agent, and for the other agent, it might be incomparable.
Have you got any intuition about how you could use this to drive the search towards the good Copeland solutions? Because that's what we would like to do with it.
So this is completely blind. So it's really, and driving, we've played around with heuristics for those problems, like choosing the high utility values first, and that will be counterproductive because you really get a skewed sample from that. And so we have this trade-off. Trying to do it right made it actually worse. So no, we have no good answer yet. But that would be important. Yeah.
Do you think it would be possible to do this for a bit, to then kind of learn what the Copeland solution might look like, and then basically transform the utility functions into ones that have a common currency, because that would then allow you to maximize them together and actually.
Yeah, I also thought of doing things like, okay, if there is a better solution out there, it's very unlikely that it won already against, or that it now lost to 10% of the pool. So we can post this as an additional constraint as well. So we could say you have to be at least better than something like this, so you get at least a bit of propagation. But yeah, this idea of converting it, I hadn't thought about.
All right, it's the next speaker again.